So I will give a talk about Dicke superradiance. It's not the first one, as you know, and I might add a little bit to the confusion because I link now superradiance to another completely different topic, namely Hanbury Brown and Twiss intensity interferometry, something which you would not probably expect. But by doing this, I hope at least to clarify some points which have been discussed here in the past, which have been heavily debated. I remember by Jamir the comment from the first day, you remember, that superradiance might be a classical effect. And I heavily protested. I mean, the really original idea of Dicke does not involve any classical effects, even though nowadays 90% of the phenomena you were describing and people are describing are maybe linked more to classical effects than to quantum effects. And this really is a big confusion. It is not unknown. I mean, this confusion is known from well-experienced people since the 70s. That's written up in books, so you can read it up. And I will touch this aspect as well, but bringing a new twist into the whole discussion, namely linking the whole thing to the Hanbury Brown Twiss intensity interferometry. Okay, so just to recover one aspect, I mean, we are discussing also heavily, of course, in the context of this conference. This is a modification of spontaneous decay, which is linked to Dicke superradiance due to collective effects. And I just want to remind you, of course, that spontaneous decay is usually considered to be an effect which is, first of all, isotropic. And for each atom of the same species identical and of course cannot be modified. It's an exponential decay in time and isotropic. But we know, of course, since a long time, since decades, that this is not true. You can modify the spontaneous decay by changing and altering the boundary conditions. This is known, of course, under the name of cavity QED, and this has been heavily discussed also in this conference. And this cavity QED nowadays has approached a new field, I would say, which has been established since also a longer time, but not infinitely long time. This is a waveguide QED, so to say, where people realize that a lot of modification of spontaneous decay cannot only be realized inside of a cavity, but putting emitters next to a waveguide, as we have seen yesterday, for example, by the beautiful talk by Wahid, but many other contributions as well. So this is a new field, but also what is true and has been also heavily discussed in this context, in particular, as one of the main features of the conference, that spontaneous decay can also be modified by atomic correlations. And so there is even a mapping, a kind of mapping between cavity QED and correlation QED, if you would like to say, the modification. And of course, we know nowadays that a single atom is emitting in free space, might not emit in free space, even in free space isotropically and even modified in time, if you consider correlations. And this is exactly the idea of superradiance, as proposed by Dicke and put forward more than almost 70 years ago. So this, what is really nice with this paper is it still stimulates thoughts and debates, even on this conference. What is superradiance? And so it is really a remarkable paper, I would say, a really fantastic paper. And of course, I list here only a few canonical papers, and you can see they're very old, sometimes 50 years old. And there has been a huge, tremendous amount of literature on this topic, and even raising in the recent years, because we now can realize correlations in the lab more easily than in former times. There have been still few experiments, I would like to say, but sketching up. And so this discussion in the context, of course, also of bringing condensed matter physics and atomic physics together, where many body phenomena are discussed and brings this idea of superradiance more on the table again. Okay, and now my twist here is that I bring together these two papers. Both of them are almost 70 years old, I mean, very astonishingly. And certainly Hanbury Brown Twiss and Dicke would have not known each other. And and this is also, I should say, a very important paper for quantum optics. Some people consider it even as a foundation paper of quantum optics, because Roy Glauber catched up this idea. He was completely puzzled by this idea of Hanbury Brown Twiss interference to photon interference. He could not understand what this really is, and he put forward a very nice theory and got a Nobel Prize in 2005, as you know about this. They were astronomers. They would not even known that they would give a contribution to quantum optics, but they did. And in particular, they would certainly not know that Dicke, at the same time, more or less, put forward a paper where they described more or less the same effect. So I just wanted to, and I will tell you later on how this can be understood. Okay, so this is the overview of my talk. And the first part I will discuss, as announced, a little bit this idea of coherence at different degrees. Very briefly recapitulating this idea of Young interference, what is the most famous and well-established idea of coherence. Then I have a brief look at Dicke superradiance, where another kind of coherence pops in, a very different one from the one of Young interference. And I make a first link to the Hanbury Brown and Twiss effect, which we will then discuss in the third part more extensively after having discussed in more detail what superradiance, at least from the canonical point of view of Dicke, is about. Okay? And especially in this part, I will clearly make out that this is not a phenomenon which you can describe classically, because all the states involved in this phenomenon are entangled states, highly entangled states. Okay, so catching up very briefly, of course, you know Young's double slit, the first order interference, coherence, as we say it, a spatially coherent beam impinging on two slits, producing a stationary interference pattern in the far field, which we call the first order correlation function, or the intensity distribution here, and which scales with the distance of the two slits and produces an interference pattern due to the coherence, spatial coherence of the first order coherence of this impinging beam, a laser beam, for example. Now we can describe this also on the single photon level, then not instead of a laser beam, we would have a wave function, spatially coherent, that's important. And then the photon has the two passes in the quantum path description, either to go the upper or the lower way path with a relative phase in between. And again, we produce the same kind of interference pattern for the probability to detect a photon. And of course, if you accumulate many, many photons, then we end up in the same intensity distribution in the macroscopic limit as in the macroscopic coherent beam of a laser. And this goes back and can be explained, of course, with a statement which all of you might know very well. Each photon interferes only with itself, and no interference between different photons ever occurs. Okay, so this is well established, and we can go one step further, going down to replacing the two slits by two atoms, now coming into the field of atomic physics, so to say, and even many body physics, I mean two bodies, two elements here, which also may scatter light, and this has been beautifully done 30 years ago in the group of Dave Wineland, where they had two mercury atoms trapped in a Paul trap, cooled down so that the jiggling of the atom has been reduced very much, illuminated coherently with the laser, scattering coherently the light. And so, no surprise, in fact, you get an interference pattern of the scattered photons in this idea of Dirac on the slide before. Accumulating many, many photons gives this interference pattern produced by the atoms. Now, with the atoms, we have to be a little bit more careful because they don't only scatter coherently, they also, as we know, scatter incoherently, what we call fluorescence light. So the fluorescence light is incoherent, and so this depends on how strongly you drive the atom, as we will see a moment later. So if you drive the atoms very strongly, most of the light is incoherent because you produce really fluorescence light. Whereas if you drive the atoms very decently, as has been done in the experiment on the slide before, most of the light is scattered coherently, and this is exactly what has been exploited in the experiment of Dave Wineland, which I just showed, and which I will not exploit in the future. I will exploit this fluorescence, completely incoherent fluorescence light, and discuss the way we can produce interference patterns even in this case. Okay, so this is the G1 function, the intensity distribution now for two atoms, again, scattering as a function of saturation. And you can see this coherent interference pattern, which I showed on the slide before, really with a visibility of 100%, vanishes if you drive the atoms very, very strongly, because most of the light is then scattered incoherently. You don't have any more a fixed relationship between the two paths the photon can take, because it's fluorescence light. And so in that case, the visibility drops down, and you can even derive that analytically, and it goes down the visibility with 1/s more or less, and vanishes completely if you drive the atoms very, very strongly. So we did this kind of experiment. We redid the experiment, so to say, of the Wineland group in 2016. Again, in the first part, having coherently light, I mean, driving the atoms very decently, producing a nice interference pattern, very much as in 1993 by the Wineland group. But then we went into the regime where we drove these atoms very strongly. And here you can see the visibility indeed goes down as prescribed by the theory and vanishes then if we drive them very, very strongly on this transition. I should say we stored 2 calcium atoms in that case, which are driven by this transition at 397 nanometers. Here's a repumping laser, we don't care so much. So we drive these atoms on this transition here, and the stronger we drive, the smaller becomes the visibility of this interference pattern. So this has been nicely reproduced. And you can understand that in the extreme case where you don't drive the atoms very strongly, but you have a pi pulse bringing the atoms from the ground state to the fully excited state, so that only fluorescent photons are produced by these 2 atoms. So if you bring both atoms initially into the excited state by a pi pulse, then, as I said before, the phases of each emission, each path which can be taken, is completely random from shot to shot. So there's no fixed phase relationship because we don't have anymore the spatial coherence as in a laser beam. And so for a single emission process, we produce an interference pattern, stationary, that is true. But for the next shot, the next pulse, so to say, this can be shifted because from shot to shot, as I just said, these phases are not fixed. And if you do many shots, then of course you don't get any information anymore, no interference pattern at all. The intensity is completely isotropic, as you would expect from fluorescence light. So we have lost, in this case, this aspect of spatial coherence and are incoherent in this case. And you can even calculate that quantum mechanically, where you replace or describe the field here in the far field as a superposition of each atom with a lowering atom, accumulating a certain phase from atom 1 to the screen or atom 2 to the screen, which is incorporated in this phase here. Start from the initially double excited state and calculate the whole thing, and this is indeed a constant. So this is a mathematical calculation, but you can understand it more easily even from a different point of view. That is the which path information which you can obtain in the case you start from a double excited state. Because if a photon is emitted, in that case, what you will have starting from the double excited state, that either the first atom or the second atom is in the ground state. So you start from the same initial state and end up in 2 possible final states which have no overlap at all. They're completely orthogonal. And from this point of view, quantum mechanically, you understand there are 2 paths, but they don't come to the same final state. So no interference fringes are expected. And this is confirmed by the theory, as you can see here. Now, I turn to the description of dipoles, coherently oscillating dipoles, which has been discussed many times in this conference, where you can also try to, so it's not the double excited state I'm looking here, investigating if 2 atoms are in a coherent superposition of the ground state and the excited state, so they would display a dipole moment, okay? So 2 dipoles oscillating, this is a quantum mechanical description of 2 dipoles even oscillating in phase. And you do this very simple investigation of which path information, which is more quick. You can calculate it, of course, also, but this which path information tells you already if the first atom, for example, emits a photon, it will go from this state here to this state here. You can see, so this is the consideration that the first atom has emitted a photon or the second photon has emitted a photon, and the 2 final states which are possible do have an overlap. So you would expect an interference pattern, and if you do the calculation, indeed, you have a nice interference pattern where the visibility depends then on the parameters alpha and beta and can be maximal, and so you understand how in the case of coherently oscillating dipoles, again, you recover an interference pattern which you will not recover if you start from 2 double excited states, or as we just discussed. Okay, so so here we have a classical explanation of the whole thing. I press a button, maybe I was too fast. So the question is, what about a Dicke state? Okay, and a Dicke state is this state described here, vulnerable symmetric Dicke state over here. Would we produce an interference pattern in that state? I should say that here is no dipole moment, as I will discuss later on the slide as well. No dipole moment. So this state displays no dipole moments. Either the atom is in the excited state or in the ground state. No coherences at all. And from a quantum path picture, you have now 2 possibilities from this initial state to end up in the ground state, and in the same ground state, by the way. And so you would expect to obtain full interference visibility. And this is indeed what you obtain also in the concrete calculation. If you calculate the first order correlation function starting from this state, you get a nice interference pattern, even with 100% visibility. And this produces all the confusion, because people think of oscillating dipoles. This should be something like superradiance. No, it's not superradiance, as I will explain later. Superradiance is linked to these Dicke states. So superradiance was introduced in the Dicke paper. He introduced in the same paper the Dicke states. This is one of the Dicke states. They produce nicely an interference pattern, but not at all involving any oscillating dipoles. Okay, so I want to make that very clear, and I will come to this later on. Now, I come back to this initial situation where we don't expect any kind of interference, a double excited state. So not oscillating dipoles, not a Dicke state, a pure state. It's also a Dicke state, but it's a pure state with a double excited. We saw already that there's no interference pattern occurring, but we can probably change the way how we detect this kind of state. And so instead of measuring just the intensity with some detector, what we would do, we would go back to the idea of Hanbury Brown and Twiss and use two detectors. So this is what they proposed almost 70 years ago in the context of astronomy, where they wanted to resolve two incoherent emitting sources, two stars. So this is also two incoherently emitting atoms, as we can. So if we boil this configuration down to two incoherently emitting atoms with two detectors, and then in this case calculate or measure the second order correlation function, then what we obtain, and we can understand already why an interference pattern should be produced, because we start from the same initial state here, but now we have two paths how to bring this two atom excited state into the two ground states emitting two photons. That is, either the first atom emits a photon going to the first detector, and at the same time the second atom emits a photon going to the second detector, or another quantum two-photon quantum path is this configuration where the first atom emits a photon which is detected then by the second detector, and the second atom emits a photon which is detected by the first detector. These differ in phase. These are two photon quantum passes, but there are two of them. They differ in phase and start from the same initial state and end up in the same final state. So again, from a quantum mechanical point of view, you would expect an interference pattern. And this is exactly what you could see here with a visibility of 100%. And you can ask yourself, is this in some way, somehow linked either to the Dicke superradiance or to the coherently oscillating dipoles, or is this any way this interference pattern linked to anything which we discussed before? And I will clarify this question in the following slides. Okay, so a small tutorial on what is superradiance. Again, as I said, for an initial atom in free space, we have isotropic emission and in time exponentially decaying probability to be in the excited state. But if we have a bunch of atoms, two-level atoms, in a volume much smaller than the wavelengths, then the whole thing is modified quite a lot, as has been discussed heavily also in the context of this conference. Okay. So upon emission of a first photon from this fully excited state here of the atoms, you detect a photon. But then you have a projective measurement where you do not know by principle, because the volume is so small, which atom has emitted a photon. So you end up in this kind of Dicke state where you do not know whether the first, the second, the third, or the nth atom has emitted the photon. So you have to describe your state as a coherent superposition of the different possibilities, which is the Dicke state. And so if you detect the second photon, same. I mean, there are two atoms then in the ground state. You do not know which one is in the ground state. So you end up in a Dicke state, which, in a coherent superposition of different possibilities, which is again a Dicke state, a fully entangled Dicke state. And so this is the ladder of symmetric Dicke states. And if you watch out the whole phenomenon as a function of time, you see a completely different behavior. It's not an exponential decay anymore, as has been discussed also in this context, but this is a peak in intensity, which in addition might emit in particular directions, as we can see, with an intensity which is scaling as n squared. And it is exactly this n squared law which Dicke in his initial paper brought to this idea. There might be spontaneous emission of coherent radiation because we obtain this n square law, which we know from a double slit or a grating where the central peak is scaling with n squared, even though the light here is emitted completely incoherently. That was his puzzle, okay? This is the title of his paper, A Coherent Emission of Spontaneous Radiation. And he thought there might be some coherent radiation. Yeah, we will see there is some coherence involved, but not the coherence you would think about usually, and Dicke was thinking usually about. And we will come to this point very quickly later. Okay, so first remark, there is no dipole moment at all in this whole system here. So this idea of synchronization of dipoles oscillating in phase as being superradiance, at least according to Dicke, is wrong, okay? I mean, you can call it superradiance. I mean, whatever you do, you can call it also whatever, but it's not what Dicke described in his paper, okay? So Dicke described in his paper this ladder of symmetric Dicke states which do not display any dipole moment at all and never oscillate in phase or something like that. So the question is, what is it? Why do we obtain this n-squared law in the forward direction even though only spontaneous emission is involved? And the answer is, again, if we look in the first order correlation function, the intensity, and if we calculate it as before as a as a superposition of the option of either atom 1, atom 2, atom 3, or atom n is emitting a photon, incoherently, by the way, and accumulating a certain phase towards the detector. So this is a total field produced by all these atoms. And we calculate this intensity, and we will see this intensity here will depend on the initial state. And to make that very clear, let's start with a very boring state, not an entangled state, the double excited state, the initial state where two atoms are in the excited state. So we have the possibility of producing intensity that either the first atom emits a photon accumulating a certain phase, or the second atom emits a photon accumulating a certain phase. These final states, as discussed, are completely orthogonal, so there's no interference occurring between these two states. And if I calculate the intensity, I have to take the modulo square of these two passes, and since there's no interference between the two, I end up in adding this pass modulo square, which gives me a factor of 2 here, but no interference pattern. Now, the whole thing changes if I take the same excitation, again, two atoms in the excited state, but they are not separable. They're in an entangled Dicke state. So again, two excitations, but I do not know which atoms are excited. And there's this coherent superposition, and here is a coherence occurring, a coherent superposition that either the first two, or the first and the third, or the last two atoms are in the excited state. And let's do the same calculation as on the slide before again. So for the first term, I end up in the same probabilities I was describing on the slide before. Either the first or the second atom emits a photon accumulating a certain phase, ending up in final states which are completely orthogonal. The same is true for this term here. Here it's either the first or the third atom which emits a photon accumulating a certain phase. They're completely orthogonal, these two states. And of course, the same is true also for the third term. Here it's either the second or the third atom emitting a certain phase. And these states are completely orthogonal. But due to this coherent superposition of these options, we find that these two states, for example, they are the same and they might interfere. These two states are the same. They might interfere because they're different phases, and these two states might interfere because they're different phases. And it is due to this kind of coherence, which is not a coherently oscillating dipole, synchronized dipole. It is entanglement of the state which produces a coherence. Okay, so this is an essential part to understand what is superradiance in the case of Dicke. So if we calculate the intensity, then we have indeed interference, as I just said, interference between different paths which might occur. And if we do the calculation, then indeed we obtain a completely different result, a result which is double as high as in the case of the separable state, due to the fact that we have this coherences which we take into account due to the entanglement of the state. And if we do the entire calculation, that is, we take into account all the different final states. In the last slide, there were 3 different final states of a particular configuration into account. The number of passes producing or leading up into this particular final, into a particular final states, and the normalization, we end up in a very simple formula, which is exactly the formula derived by Dicke in his famous paper. Okay, so Dicke relied on this kind of argumentation in his famous paper. And indeed, you can see if you're halfway through, half of the number of atoms is excited and half of the number of atoms are in the ground state, but you do not know which ones, of course, because you're in a Dicke state. Then you have this famous n-squared law, which puzzled Dicke and which has puzzled many people here also on this conference. Okay, but again, I point out very clearly, it is not due to coherently synchronized, coherently oscillating dipoles. It's due to the fact that we have entanglement in the system. Now, if we take into account the phases I was referring to, so far I looked only for the maximum intensity. If we take into account the phases, phi 1, phi 2, phi 3, if you remember, and do the same calculation, we also see that this coherent spontaneous emission produced by each individual atom in this configuration of correlated states, entangled state, will produce a spontaneous emission pattern scaling with n squared, here in the case of half of the atoms in the ground state and half of the atoms in the excited state, but it's peaked into a particular direction. So it's spontaneous emission, but it is peaked in a very particular direction. So the directionality comes also in very naturally in this analysis. Okay, what I plot here is the most surprising effect. That is, if only one atom is in the excited state and the rest of the atoms are in the ground state, but you do not know which one, you don't have an isotropic distribution, as you can see here, but you have an interference which produces then proportional to n. Well, we are not on halfway through the symmetric states. We are almost down the ladder, only one excitation, but it's proportional to n, very peaked direction, and is proportional to n, even though only one excitation is in the system. Okay. Okay, so with the same argument, you can, of course, also describe subradiance. In this case, in the forward direction, instead of having a peak, as a situation we just discussed, you have a minimum here in the forward direction for particular Dicke states which are non-symmetric. And so we can explain also in this way subradiance. Okay, so now that we understood what superradiance is really coming from, we can go to this argument, what is the link to the Hanbury Brown and Twiss effect I just announced in the beginning? How does this anyway have something to do with sticky superradiance? And we generalize our system. We are not producing the second order correlation function, but the mth order correlation function where we have m detectors here, n sources here. So this correlation function which involves m times the intensity recorded at these m different detectors. And we can ask ourselves, oh, wow, okay. And we can ask ourselves how this can produce superradiance. And so we will see in particular on the next slide that this can be easily understood, in particular the example which I gave, where two atoms are in the excited state and two photons are detected. So these are very far apart, okay? So they are not interacting at all, but I detect the photon in the far field, such that the detector cannot know whether the photon comes from this atom or from this atom. So if I detect a photon start from the fully excited state, I will end up in a state where one of the atoms are in the ground state, but I do not know which one of the atoms is in the ground state. I have to take into account the relative phase of these two options, and I will see that I end up in a Dicke state. Now, if I detect the next photon, then I obviously detect the intensity of this particular state, and we know already what this produces. It produces an interference pattern of this kind, because I start from a Dicke state. I start from a state which displays superradiance. I detect this superradiance, and it coincides with a law derived by Dicke, where I have one excitation and one atom in the ground state, as you can see here. So the maximum is 2, which I produce in the forward direction, which coincides with this formula. And this is really what I observe as superradiance. But at the same time, of course, it is also the second order correlation function, and which usually is, the configuration of an HBT, Hanbury Brown and Twiss experiment. So we can see at this point that these two phenomena, here's an inequality, are completely identical. So superradiance, or I should say Hanbury Brown and Twiss interference, is a kind of projective measurement at the first place. And then I measure this correlation among the stars or atoms which I produce, which then produces a superradiance. And this is exactly the HBT interference which has been discussed since and exploited since many, many years. Okay, I can do this, of course, for, as I announced, for many atoms, n atoms, m detectors. And if I detect one photon, I end up in a Dicke state with 1 de-excitation. If I detect a second photon, I end up in a Dicke state with 2 de-excitation, and so on. And if I measure m photons, what I measure is the intensity of a Dicke state with m-1 atoms in the ground state, but I do not know which one. And this is this described here. But at the same time, of course, it's the mth order intensity correlation function, which I can calculate in the way I described already. So this is a number of different final states, which I have to take into account the different passes ending up in a particular final state, which make interference among the two, among the different options, and produces interference pattern. And so I don't know how much time do I have, sir?
Minus
Oh!
4 minutes.
Of -4, okay, then I will end up with these two slides, if I may. Okay, so it's a very easy calculation if I have put my M-1 detectors at the same place. I have an analytical formula which shows that indeed in the forward direction, and as a function of the number of emitters here, I get a peaked, as is n equal 2, 5, 3, 5, 10, more and more peaked emission in the forward direction with a visibility of 100% if the number of atoms is equal to the number of detectors. And so I modify the spontaneous emission dramatically. Okay, so I think I accelerate. And I would have liked to detect, okay, so I would have liked to tell you also something about thermal sources, where this is also true, this idea, but we leave that out for the moment. And so I come to the conclusion that spontaneously emitting single photon sorters in entangled Dicke states emit super or subradiant light. And superradiance can be understood as a consequence of single photon quantum passes constructively interfering in case of entanglement and entangled Dicke states. And so we had some experiments, which I did not show. I think it is more important to discuss the theory here in this context. And so in particular, we made the link between superradiance and HPT measurement and found that HPT and superradiance are simply two sides of the same coin. And I would not like to finish without saying that there are, of course, many, many people contributing either in the past or presently to these investigations. I would like to highlight in particular my collaborator Stefan Richter, who will submit his defense, his PhD thesis next week. And so here are some slides of my group. So this is Stefan Richter, and with this I thank for your attention. Okay, I'm sorry.